We are going to take some provided equations right now, and we are going to write the equations of any horizontal or vertical asymptotes that may exist. So a few things that you should take note of. For starters, the numerator and denominator of each of these functions qualify as being polynomial expressions. So poly, many, nomial terms, they all will have whole number exponents. For the x, 2 is a whole number, 1 is a whole number. This is really x to the 0, and 0 is a whole number. So we have polynomial on top and bottom, and right now the numerators and denominators are all written in standard form, meaning they are in descending exponential order. If you are looking for a horizontal asymptote, remember this is not a full lesson, this is a review of algebra concepts. If you're looking for a horizontal asymptote, you want to pay attention to the degree of the numerator and the degree of the denominator, the greatest degree, both on top and on bottom. So in Algebra 2, you learned a few shortcuts. This is something called end behavior that we're analyzing right now. You're looking at what happens way out to the right when x is getting closer and closer to infinity, and what happens way out to the left as x gets closer and closer to negative infinity. So if we're paying attention to this part of the problem, what we don't want to pay attention to is really the rest of it. If we have 2x squared over x to the third power, we can even kind of imagine that being reduced as 2 over x, okay? Now, end behavior, 2 over x. Imagine plugging in bigger and bigger numbers for x. Say I plug in 100, I get 0.02, 1,000, 0.002, and so on. So as x approaches infinity, comma, y approaches 0. How about the other way? Going to the left, okay? I'm going to still write it this way, but I'm going to say as x gets closer to negative infinity, which is that way, okay? Going out this way. Well, now it's 2 over negative 100, 2 over negative 1,000, 2 over negative 1 million. Y is still going to get smaller and smaller, my output value, so I'm still approaching 0. That means that my horizontal asymptote is at y equals 0. The way you learned it in Algebra 2 was if the degree on bottom is bigger than the degree on top, your horizontal asymptote is at 0. Boom, done. You don't have to do this. You can immediately just write that down. Finished. How about this one? The degree on top and the degree on bottom are equal. And that happens. Again, you're still ignoring this. You're paying attention to this. These essentially even reduce. This is not really ever how you reduce something. This is just a trick. When in Algebra 2, what you learned for horizontal asymptotes is that when the degree of the numerator and the denominator are equivalent, your horizontal asymptote is at y equals the ratio of the leading coefficients. That means negative 3 over 1. A ratio is a fraction or proportion. Negative 3 over 1 is negative 3, and that is where our horizontal asymptote is at. How about here? Here you need to know this is an x to the 0 on top. So I have a 2 on bottom and a 0 on top. The degree on bottom is larger than the degree on top, so my horizontal asymptote is at y equals 0. Done. Next, we have vertical asymptotes. Alright? Now, vertical asymptotes you get by basically drawing these dotted lines, and they're both dotted lines, but they're not created the same way. These dotted lines where x is not allowed to have graph, where our restrictions are. Basically, any interruptions in our domain that are not removable discontinuities, meaning they don't factor out and cross out from top and bottom, they don't reduce out. We just draw a dotted line there, and we call that line our vertical asymptote. So, let's see here. This example, this is actually the sum of 2 cubes. Okay, a little refresher, but when we have x cubed plus 27, 27 is really 3 cubed. You look at it like this, and we factor, again, I have videos on this explaining how to factor this. You can find them underneath the polynomial section. It might be solving polynomial equations, so if you need practice on factoring something like this, please go check that out, okay? X cubed plus 3 cubed, that's going to give me an x plus 3 right here, and then this factor, x times x is x squared. This is my trick. X times 3 is 3x, and then 3 times 3 is 9. This is the same sign as the original This is always the opposite, and this is always plus. This does not factor, nor does it have any real solutions. If you use quadratic formula, you get imaginary answers. So if this never equals 0, it causes no issue in my denominator because the domain restrictions come from the fact that you can't divide by 0. So this is the only one I have to worry about. X cannot equal -3 because that will make -3 plus 3 will equal 0. So I have a vertical asymptote at x equals -3. I'll have a dotted line there. Vertical asymptote. B, this one over here. This is a bit more of a classic quadratic. I know I crossed it out in pink, but let's use our imagination and pretend that that's not there. X, 4, and 1. Here's -4, here's +1. Now if I set each of these equal to 0 to find out what x cannot be, we will learn that our vertical asymptotes are at x equals -1 and at x equals 4. If either of these factors were factors of the numerator, which they are not, I promise, and crossed out, they would not be vertical asymptotes. They would be a hole in your graph or removable discontinuity. Okay, so we're good up to there. C. If I try to factor this, it's actually the sum of two squares. This never equals 0. If you think about x squared plus 4, it's just the parabola moved up 4 units. It never equals 0. So this graph right here has no vertical asymptote. Okay? A few more examples to practice. Okay, these three we're going to try to get through quickly right now. Horizontal asymptotes, degree on top and bottom are the same. It's going to be at y equals 1. Next, I didn't mean to do this, but I'll change this one then. Make that a 3. They're the same again. Horizontal, y equals 1. That's my horizontal asymptote. Here, bottom's a 3, top is a 2. So my horizontal asymptote's at y equals 0. If the top power were bigger, you would have something called an oblique or slant asymptote. Slant asymptotes you definitely did in Algebra 2. That would be something you would find when the degree on top is greater than the degree on bottom by exactly 1, and you would do long division. Sometimes you could do synthetic, and you would ignore the remainder, and that would be your linear equation, would be your quotient, other than the remainder part, and that would be your slant asymptote. Vertical asymptote here is x equals 3. Here, if I factor this, I'll get an x plus 4 and an x minus 4 on top. On bottom, I get an x minus 4 and an x minus 5. If you didn't pay attention to the top and only worried about the denominator, okay, you might write that you have a vertical asymptote at 4 and at 5, but really this reduces. So there's a hole when x equals 4. We only have a vertical asymptote at x equals 5. And here, I just have plain old x to the third. My vertical asymptote is at x equals 0. Alright? So that's the end of our little crayon session on horizontal and vertical asymptotes.